In this video, we are going to talk about intermolecular forces. First of all, intermolecular forces are defined as attractive forces experienced between two or more molecules or atoms. Of course, a molecule is when you have two or more nonmetals which are bonded together with a covalent bond. Generally, intermolecular forces are a weak electrostatic force, which means that the molecule has a partially positive region and a partially negative region. And the partially positive region of one molecule will form an interaction with the partially negative region of a different adjacent molecule. Now, it's very important to appreciate that intermolecular forces are not the same thing as chemical bonds. Chemical bonds, such as covalent, ionic, or metallic bonds, are much, much stronger, and they hold the atoms together with much more strength. Intermolecular forces are much weaker and generally more temporary interaction. You can see here that the strength of an ionic bond is about 500 to 1,000 kilojoules per mole. So that's about how much energy it takes to break an average ionic bond. A covalent bond is also very strong. It takes about 200 to 500 kilojoules of energy to break a covalent bond. You can see that an intermolecular force only takes about 1 to 50 kilojoules of energy to break one of those, depending on the type that we'll discuss later. So these intermolecular forces are much weaker, and again, they are not chemical bonds. So when two molecules form, or two atoms form an intermolecular force, it is not a chemical reaction. A chemical reaction only occurs when a covalent, ionic, metallic, a chemical bond is broken or formed, and you get a new substance. Intermolecular forces, when they form or break, you are not undergoing a chemical reaction. So intermolecular forces are responsible for a lot of different physical properties of a substance. Now, they're not responsible for the chemical properties. Those are determined by how the atoms are chemically bonded together. But intermolecular forces determine a lot of physical properties of a substance, such as the substance's melting point. That's the temperature at which it undergoes a phase change from solid to liquid. Intermolecular forces determine a substance's boiling point, temperature at which it converts from a liquid to a gas. They also are responsible for a substance's viscosity, how thick or viscous a liquid is. They are responsible for determining a substance's surface tension, which is basically how much force it takes to spread that substance out. And they're also responsible for a substance's vapor pressure. If you have a liquid in a sealed container, some of the liquid will evaporate and go into the gas phase. The more liquid particles that go into the gas phase, the more vapor pressure you have above that liquid. So these are some of the important physical properties that are determined by how strong or weak a substance's intermolecular forces are. So take a minute and predict the relationship between intermolecular forces and these physical properties. So for example, if a substance is able to form strong intermolecular forces, if the molecules can form strong intermolecular forces with other molecules, will it have a high or low melting point, boiling point, viscosity, etc.? So take a minute and predict that relationship. Okay, so let's talk about some of these physical properties and their relationship to intermolecular forces in just a little bit more detail. First of all, let's take a look at melting points and boiling points. In general, substances where the molecules can form strong intermolecular forces with other molecules, these substances tend to have high melting points and high boiling points. And think about it, if the molecules in a substance, let's say it's a solid, and the molecules form strong intermolecular forces with other molecules nearby, that substance is more likely to be in the solid phase. And if these intermolecular forces are very strong, then it takes a lot of energy to get these molecules to break free of these intermolecular forces and go from the solid to the liquid phase. So if you increase the temperature or increase the energy in these molecules by increasing the heat, their molecular motion increases, and eventually they get enough molecular motion to undergo a phase change. The stronger the intermolecular forces, the more energy it takes to disrupt these intermolecular forces and cause this phase change. The same thing with a boiling point. Um, if a substance is a liquid and that substance has strong intermolecular forces, then you have to put a lot of energy into into these molecules so that they gain enough kinetic energy to overcome these strong intermolecular forces and undergo a phase change from a liquid to a gas. Um, if that substance has weak intermolecular forces, then the molecules do not interact with other molecules very strongly, and it doesn't take a lot of energy to result in to have a phase change occur. Just to illustrate this, let's just take a second and look at this heating curve. Just real quick, we have on our x-axis, we have heat. Heat is a form of energy, so as we go from left to right, we are increasing the heat energy that we put into this system. And as the heat increases, generally the temperature of the substance will increase. So on our y-axis, we are plotting temperature. So this is a heating curve for water. And if you look at the very beginning down here, we have water at negative 40 degrees Celsius. So obviously that's going to be in the solid phase or ice. And as we begin to increase the heat into this system, the molecules, the molecular motion increases, and this causes increased friction, and the temperature of the ice will begin to increase. And so eventually, as we continue to put heat into our ice, eventually you get enough heat in that the molecules have enough kinetic energy that they begin to overcome or break free from a lot of these intermolecular forces holding the water molecules together. At this point, the ice begins to melt. So right here, the ice is undergoing a phase change from solid to liquid. Now, it's very important to note that if you look, we're continuing to add heat, but the temperature is not increasing. So this line is flat or plateaued. So we increase the heat, but we're not increasing the temperature. The heat is going into breaking or disrupting some of these intermolecular forces. Now, once you've disrupted a sufficient number of these intermolecular forces, then our phase change is complete and the ice is melted or converted into water. Then if we continue to add heat, the temperature of the water will continue to increase, as you can see here, until eventually we again add enough heat that we begin to undergo another phase change. So we add enough heat that the molecular motion of the molecules, again, it has increased sufficiently that they are beginning to break free of all of the intermolecular forces holding the molecules together. At this point, we begin to boil or undergo a phase change from a liquid to a gas. And as you notice, again, we have a flat plateau. We're adding heat, but the temperature is not increasing. The heat is being used to do work or break the remainder of these intermolecular forces holding the water molecules together. At this point, at this phase change, you have an equilibrium. At this phase change and the melting phase change as well, the liquid and gas particles are in equilibrium. Eventually, you add enough heat that all of the intermolecular forces have been disrupted, and our water is fully converted into a gas or steam. then we continue to add heat and the temperature again begins to increase. So take a look at this heating curve and familiarize yourself with it, especially these phase changes, and appreciate why we have a plateau at those. Now, so we talked about melting points and boiling points and their relationship to intermolecular forces. We're going to briefly talk a little bit about the other physical properties. We mentioned viscosity is a property that a measure of a liquid's resistance to flow, and molecules that form strong intermolecular forces tend to have high viscosity because the molecules stick together very tightly so they don't flow very evenly. So here you can see the blue liquid looks like it has a fairly low viscosity. It flows fairly readily. So we would predict that the molecules in this liquid don't form very strong intermolecular forces compared to this yellow substance, this yellow liquid, which tends to be very syrupy, very thick, have a very high viscosity. So this substance over here on the right, the yellow liquid, looks like it has a much higher viscosity because it has a much higher resistance to flow. So these molecules in this liquid would probably have very strong intermolecular forces compared to the blue liquid on the left. Now we also mentioned that surface tension is a physical property that's determined by the strength of intermolecular forces. And the relationship there is that molecules that form strong intermolecular forces, they tend to have a high surface tension. Here you can see a picture of a water droplet. On the interior of the water droplet, over here on the right, the molecules are able to form intermolecular forces all around them. On the surface, the molecules that exist on the surface, if we look over here on the left, the molecules on the surface can only form intermolecular forces with the molecules to the side and below them, because there are no molecules above them. So that tends to deform or cause the liquid to form a kind of a spherical shape. That's why water and different liquids tend to form droplets. So the more spherical these droplets are, that tends to indicate that there's a higher surface tension, which results from stronger intermolecular forces. And that's actually a measure of surface tension. Liquids that tend to form very flat droplets when put on the surface, they don't form very strong intermolecular forces, and so their droplets are much less spherical. And the final physical property that we want to talk about in relation to intermolecular forces is vapor pressure. If you take a liquid and you put it in a sealed container like we have here on the left, some of the liquid molecules will start to evaporate or go into the gas phase. If you leave it for a sufficient time, eventually you'll have enough liquid particles enough liquid particles will go into the gas phase that you reach an equilibrium. What that means is that for every one liquid molecule that goes up into the gas phase, one of the gas particles will condense and go back into the liquid phase. So you have this equilibrium. Every time one liquid molecule evaporates, one gas particle will condense back into the liquid phase. So you have a equilibrium that's reached. Now, because you have a gas above the liquid, gases, of course, exert pressure. And so the more gas particles you have, more particles you have in the gas phase, the higher the vapor pressure. The fewer gas particles you have in the vapor phase, the lower a substance's vapor pressure. So substances that tend to form very strong intermolecular forces, most of the molecules tend to remain in the liquid phase and not in the gas phase. So the vapor pressure would tend to be low. Molecules that form weaker intermolecular forces, the molecules are much more likely to evaporate because they're not sticking together very tightly, and so the molecules will be more likely to evaporate and go into the gas phase. So if you have more molecules in the gas phase, then you have a higher vapor pressure. So the relationship there is molecules that tend to form strong intermolecular forces tend to have lower vapor pressures. And finally, we just need to ask the question, well, what what determines the strength of an intermolecular force? Some molecules form weak intermolecular forces, some molecules form strong, and of course some are in the middle. We'll talk about the types of intermolecular forces later, but in general, an intermolecular force is an electrostatic interaction. As we mentioned before, two molecules may have a partially positive and partially negative region. So they're not ions now, they're not positive and negatively charged. They tend to have a partially positive region, a partially negative region. And so what causes them to stick together strongly are a couple of things. First of all, the magnitude of the charges. Some molecules have a very highly positive region and a very highly partially negative region. In other molecules, the partially positive and partially negative regions are much lower magnitude. So molecules that have very highly partially positive and partially negative regions, those tend to stick together much more tightly. So Q1 and Q2, the magnitude of the charges would tend to be high. That would give them a strong attractive force, which is represented here by F. The other thing that determines the strength of an intermolecular force is the distance between the two charges, or the distance between the molecules. So molecules that maybe they tend to be smaller, they can get closer together, and the closer together the positive and negative charges can get, the stronger the interaction. Just like if you hold two magnets significantly far apart, there's no attractive force. As you move them closer and closer, the attractive force between the two magnets gets stronger and stronger. That's because the distance between the two charges tends to be decreasing. So keep this in mind. When you are trying to determine why a molecule has a strong or weak intermolecular force, we need to think about two factors. The magnitude of the charges. So does that molecule, is it highly polar? Does it have a very strong partially positive and partially negative region? Is it very polar? And then also, how close can the two different molecules get together? How close can they come together? So this concludes our talk about intermolecular forces. Thank you.